with Bob's public key and send it to Bob. And in theory, no one who intercepts that message should be able to decrypt it, because the only number in the world that should be able to reverse the effects of Bob's public key is Bob's private key, thanks to a nice intertwined relationship between those numbers using something like RSA, or in the case we'll look at, Diffie-Hellman. And then Alice and Bob can communicate conversely in the opposite direction, with Bob using Alice's public key. So this is great, because this means when I, a user, visit Amazon.com and check out for the very first time, I obviously don't know anyone at Amazon, I might not have visited their website before, that's okay, because as the name suggests, a public key can be transmitted in the clear, can be shouted verbally to the whole world, because its only value is for encrypting information, or, as an aside, for digitally verifying something called a digital signature. More on that in 221 and the like. So what's the relevance here? Well, if I have a public key and a private key, and Bob has a public key and a private key, it's not enough that we just have these big numbers that we can use for encryption. The idea behind SSL is that there's this whole chain of trust. And ideally, I only want to trust Bob's key if someone else has vouched for him. And in that case, it's someone like GoDaddy, or it's someone like VeriSign, someone who's at least raised the bar to say you are who you say you are, you own this domain, is really the vetting that they do. Or in the case of the pricier ones, they might actually ask for some kind of corporate document demonstrating that you are who you say you are. And this way, this is what you're paying for. You're getting a stamp of approval from someone more important than you, like VeriSign or GoDaddy, or bigger than you, that says, as an authority, you are who you say you are. So if I instead just generate my certificate myself, my public-private key pair, and start using it, what happens generally on the web if you're using an uncertified key pair? What does the user see? Yeah?
I'm just saying it's vulnerable to random attack.
OK, so yes, SSL is still going to be vulnerable to something called man-in-the-middle attack. So let's come back to that in a second. But what does the user see if you haven't paid for a certificate? You've just generated it yourself. Yeah? Yeah, so Firefox makes this look really scary, right? Firefox is atrocious. You have to click like 5 different buttons just to get past a site that has not paid for its certificate or whose certificate has expired. And I don't know if I can, there's annoyingly some websites on campus. Let's see. Let me see if I can find one off the top of my head. No, that doesn't even work. That's nice. Oh, it's also because I have no Wi-Fi. All right, so we're very secure right now. All right. So there are a non-trivial number of servers on this campus, who shall not be named, that haven't paid the like $69.99 to have a certificate for that website. There also, frankly, exist wildcard certificates, which means for $100 or $200, annoying, but cost-effective in the long run, that can secure an entire suite of subdomains. So CS50, for instance, and even 164 paid for the wildcard certificate, so we can have as many subdomains as we want. But the real takeaway here is that SSL, to some extent, it's nice by theory, this construction of this chain of trust, but it's also a bit of a scam, and it's a bit of a marketing mechanism that's been put in place. And the fact that, frankly, we as a course need to literally pay another $200 every year to renew the certificate just to have GoDaddy, of all people, say more authoritatively that we are who we say we are, is kind of become a business unto itself. But it's worth paying for so that your users don't have to jump through those hoops of user interface to actually proceed to the next screen. So in short, that's what's going on with SSL. But there's some fascinating work, and I'll try to post on the lectures page tonight or tomorrow a talk someone gave that makes pretty clear and pretty accessible just how easily SSL can still be compromised. All it does is raise the bar, but it's not the end all. Any questions on SSL? All right, so let's take a break, and then when we come back, we'll take a look at some scary looking but very sexy math. That'll get you to come back. All right, so we are back. So public key crypto, as it relates to browsers, or really any mechanisms that's using public key crypto, even if it's something like email and PGP for encryption, works by, again, having these asymmetric keys, public key and private key. And RSA, as you've probably heard, is quite common. But there's another algorithm. There's many other versions of public key crypto. But one of the easiest ones to explain as a first pass is something called Diffie-Hellman. In this case, this is a story that goes in both directions simultaneously, and actually, hopefully, will give you a sense of how relatively accessible the kind of math is, even though the numbers involved are quite big. So on the left, let's assume that Alice is standing. On the right, Bob is standing. And these two want to communicate securely. Of course, they can't just pick a secret key like the number 13 because they would somehow have to both know that the secret number is 13. And that's fine if they can chat in advance. But obviously, if Alice is Amazon and I'm Bob, we can't talk in advance as to what our secret's going to be. So we have to use something like public key crypto. So Alice and Bob in advance are going to publicly agree on two numbers, G and P. G is what's generally called a generator. In practice, it's often just the number 2, though other possibilities exist. But there's some nice properties of 2. And P is a prime number. Now, in this case, P is generally a very large prime number. But both of them have to agree on these numbers, and they can shout them across the world. Everyone else in the world can know that they're using these numbers, as well as using Diffie-Hellman. In fact, as an aside, one of the key principles of security is that security through obscurity, like not telling anyone what algorithm you're using or not telling anyone what some of the inputs to your program are, is generally not best practice. Because if the security of your algorithm just relies on secrets as opposed to complexity, all it takes is for one person to spoil the answer for someone. Whereas a computational complexity requires time. All right, so they agree on these two numbers, G and P. Again, number 2 probably, and a big prime number. And then Alice and Bob each choose one random number, big random number. Let's call it A and B respectively. Then Alice does some math. She computes the value G to the A. So this is 2 raised to the A power modulo P. So exponentiation. Now, whenever you take an exponent of something, especially large numbers, this thing can get huge fast. But if unfamiliar, know that there's actually very nice ways of doing modular arithmetic whereby you can actually raise it to a power, but not A, raise it to a smaller power, then do a mod, then another power, do a mod, then another power, so long as those exponents ultimately equal A itself. So there's nice ways of doing modular arithmetic so that your number doesn't get too huge before you do modulo prime number. So that is to say, it's actually pretty easy for Alice to compute G to the A mod P. So just so we have a variable for it, let's just call that TA. It's T sub A. That is the number Alice computed. Alice sends that across the wire. So that's what's denoted by this arrow here on the very top. She sends not A, not G, not P. She sends the computational result of that expression. So Bob does the same thing, but he does it with B. So at this point in the story, Alice has A, and she has G to the B mod P, aka TB, whatever that number actually is. And Bob, meanwhile, has B and what Alice sent him. Well, now, thanks to the ability to multiply exponents, you can actually now compute the same value at both sides. So Alice, upon receipt of G to the B mod P, she takes that whole value and just raises it to the power of A, her number, and then does a modulo P again. And thanks to nice mathematical properties, what she really gets then is G to the A times B, or equivalently G to the B times A mod P. And Bob, meanwhile, gets the exact same results. So it's done in the opposite order, but the product ultimately is the same of those exponents. So at this point in the story, Alice has a secret number A that she did not send across the wire. Bob has a secret number B that he did not send across the wire, but both of them magically have this big number, G to the A times B mod P. So what then is going to be a number that they can then use securely? Well, they have effectively come up with a shared secret. So much more sophisticated than a Caesar cipher number of 13. They now have a nice, big, seemingly random number to use that never went across the wire. So this is, in a nutshell, how you can use public key crypto to exchange information securely. They now have a shared secret. RSA is a little more sophisticated, but again, if you're liking this kind of crypto stuff, do shop at some point one of the higher level CS classes. All right, so now let's come back to a story that we hinted at earlier, and some of you might have seen, so we'll do this one somewhat quickly, but it's nonetheless always fun. So suppose you want to log into a website, and you're not supposed to. One of the fun things to do when you're bored is to try to see if the website breaks if you type in some bogus characters. In fact, if you want to try to exploit a website, what are some good characters to type into the username and or password fields of that website? So null characters. So you can actually somehow copy and paste null characters, which you can get from like a sophisticated text editor, for instance. So you can just paste those in, which normally you couldn't type easily. Even simpler. What else is juicy? Parentheses, single quotes, semicolons, double quotes. Generally, quotes are a pretty good bet, because if the website is using SQL, they probably do have some quoted strings in their queries. And if they didn't have the foresight to actually scrub user input, you might actually trigger an error. And this is where adversaries get their advantage. I don't need to compromise this site in the first 5 minutes, but as soon as I get it to crash or yield some kind of server-side error message, that means someone screwed up. And then I can focus my attention and my interests and my spare time all the more deliberately deliberately on this site and figure out, well, what sequence of bogus characters should I type in to do more than just crash the server, but rather to somehow take it over or steal some data. So in this case, here's a very common example, and some of you, if you went to Hack Night recently or last year, you've seen this example before. This looks completely ridiculous, and I actually artificially removed the bullets that would generally appear in the password field. But suppose a user does type in single quote, space, or space, quote unquote, 1 equals quote 1, but no close quote. So notice the awkward asymmetry here. I start with a single quote, but I don't end with a single quote. And that's because, on a hunch, I feel like whoever implemented this website is probably doing a query like this. And this is one of the more simple approaches you can use in PHP. The goal here is to generate a SQL string. sprintf is like printf, but it returns a string rather than printing it to the screen. So select user ID from users, where username equals quote unquote %s, and password equals quote unquote %s. So that feels reasonable. But if what I then plug into those placeholders is literally what the user submitted, very bad. Right? So if I have not scrubbed the user's input, they could have typed anything, including that cryptic sequence of ones and equal signs and single quotes. And if you think about what I did type, I started a single quote, but I didn't end with a single quote. So whatever I typed in is going to end up where this %s is. And I didn't even type in a username. So if I now do that substitution, what does that query become? Well, it becomes this. And what does this where clause evaluate to? It's a sort of vacuous truth. It's always going to evaluate to true. So what am I going to get back? I'm going to get back a whole bunch of UIDs. In fact, all of the user IDs. And if the next lines of code in the program are only checking for the presence of one or more user IDs or no user ID to determine whether the user exists, well, odds are I've just maliciously logged in to the poor guy whose UID just happened to be first in the result set, the very first person to log in. And maybe that person doesn't even use their account anymore, so now I'm into a fairly dormant account. So what's the solution here? Well, clearly the fact that I was able to finish the developer's sentence, so to speak, with those SQL queries was not the best decision. So it's a ridiculous function in PHP, but this is one way you can do it. MySQL real escape string, which pretty much puts backslashes behind any potentially dangerous characters, among them the single quotes. So what that query would look like if we escaped it is something like this, which is actually hard to parse visually, but it's actually now safe. All I did was escape the single quotes that the user actually typed into that password field. So it's this simple, but clearly people make this mistake. And in fact, I was just reading today, and I didn't look too closely at the article, but this outbreak of the Mac worm that everyone's been freaking out over seems to have been popularized in part by compromised WordPress blogs. And it always seems to be WordPress or Joomla or these very popular CMSs and such that infect the world with everything because they use stupid functions like eval. They don't have escaping going on all that often, but it's so easy to forget these things. So indeed, one of the things we talked about early in the semester, PDO, one of its most compelling characteristics is not just the abstraction you get between using MySQL or Oracle or the like. It also does all of this stuff for you. And that's huge, to just distrust yourself. So getting into the habit of not using raw PHP functions like this, but actually using a library where you can assume or at least trust that someone else has given this more thought than you might is probably your best defense. And to stop thinking about escaping, but punt to a library that's going to do it for you and do it correctly. Super easy to do. So lastly, and Yella pointed one of these out before. So there's actually two attacks when it comes to web security that are actually a little non-obvious, but you hear these buzzwords tossed around a lot, perhaps because so many people are in fact vulnerable to them. So cross-site request forgery, sometimes written with an X instead of a C. So here's the scenario. You log into something like etrade.com. You then go to some other bad guy's website, but that bad guy has a link back to etrade.com, and it uses a GET request to essentially trick you, into this case, into like buying a share of a stock. So in other words, you go to etrade.com, you log in, therefore you have a session cookie with them. And just because you leave the website doesn't mean that session cookie expires. In fact, it might not expire for an hour or a week or a year. So you're still logged into eTrade, even though you're not physically seeing that page. So if you somehow go to this guy's website and click on that link, you've just been tricked potentially into buying a stock on the other website. And you don't even have to click a link, right? He could just do an HTTP redirect on you. It could be in a form submission. He could have, even more cleverly, this tag embedded, for instance, in any of these, which is super clever, things that you wouldn't even notice or see. Right? All of those would trigger an HTTP GET request to some other website just to see if that website is vulnerable. So how do you defend against this attack? And indeed, those of you who took 50 and did CS50 Finance, odds are you didn't really defend against this attack, albeit with your fake E-Trade-like site. So how do you defend against this attack, which seems so relatively easy to wage against your users? Yeah?
Can you generate a random key every time you load a form on your own site so you know